right, everyone, so we are on page 86 in our pink packet, and we are starting our rational functions chapter. And to understand this chapter, we're going to quickly talk about the difference between what you are familiar with, although you might not have heard these words, called direct variation, and then there's inverse variation. So direct variation means as, and I'm going to change the letters here, as your x gets bigger in value, your y gets bigger in value. So something that you're familiar with is a linear equation. So as my x's get bigger, the y's get bigger, and you get a shape that looks like this. So it goes uphill. And then there's the opposite effect, that if your x's get smaller, then your y's get smaller, and you would get the other shape, right? So what we're going to talk about today is called an inverse variation or inverse relationship. And we're going to give an example of that by talking about a rectangle that has an area of 30 square feet. And we're going to use this table here to find all the possible combinations of the lengths and widths. So I could use a lot of different numbers, but I'm just going to take the nice numbers that multiply to 30. So what I'm going to do is start out with a small length, like 1, and to make an area of 30, to get an area of a rectangle, you need length times width. So I'm going to take 1 times 30, and I'd get that area of 30 there. And then another nice number that I'm going to use is 2. So 2 times 15. If I pick a length of 3, then 3 times 10. And I could use 4, but I'm only going to actually pick numbers or factors that multiply to give me 30. So I'll jump to 5, and then this would have to be 6. And so what I want you to notice is this time, as my x's get bigger, the y's are getting smaller, and that's called an inverse variation. So if I picked 6, then this would be 5. The next nice number that I would pick is 10, which gives me 3, 15, which give me 2, and 30, which give me 1. So as the x's, which we'll put our lengths down here, get bigger, our widths, which we'll graph as the y's, get smaller. And so I'm going to kind of estimate some of these points, but 130 might be about here, and 215 would be about here, because if you notice my scale is going by 3s here, I realize this is really small to see. And then 5 and 6 would be about here, and 6 and 5 would be maybe about there, and 10 and 3 would be about here, 15 and 2 might be about there, and then 30 and 1 would be right about there. And you get this curve shape, which should look really familiar to us, because this looks really similar to our, what's the word I'm talking about? Our exponential and our log functions. So from there, we can make an equation out of that, right? So to get this, if I wrote the equation, it equals y, right? What I need is what's this constant number between these two, and that I always got 30. So to get my y value, which would have been these, I would have had to take these numbers, right, and have 30 divided by 1, 30 divided by 2, 30 divided by 3. So I'll take 30 and always divide it by the x value, and that's how I get the y values. So another way you could have looked at that is it took x times y to get the 30, and to solve for y, I just move the x over by dividing. That's probably how I should have explained it the first time, and I get 30 over x. And so this, again, is called an inverse relationship, even though it doesn't mention up here, and this introduces us to our shape of rational functions. All right, it says it right here, inverse. All right, so what we're going to do is take a look at our first rational function. And every function we've graphed so far this year has had a parent function. So this time our parent function is going to be 1 over x, all right? And so I know it has -3 and 3 here. We usually left those out, so I'm going to go ahead and take those out. And we're going to be taking these values, putting them in for x, so that we can get our y's. So if I put -2 in here, then I get -1/2. And if I put -1 in here, I get -1. And if I put 0 in here, if you actually take your calculator and you take 1 and divide it by 0, you're going to get something about domain message. You can't divide by 0. You can divide 0 by something, but you can't take a number and divide it by 0. So this point will actually not exist. And then I'm going to put 1 in here, and I get 1, and put positive 2 in here, and I get 1/2. So two big things. 0 will never result in a number because you can't divide by 0. And then I also want you to recognize this pattern of -1/2, 1/2, -1, 1. We've always kind of seen some type of pattern with the y's when we've been making our graphs. So I'm going to graph my points, and this is a really small graph, but here's -2, -1/2, and here's, whoop, sorry, didn't even graph that right. Oh well, I'm going to switch colors then. Here's -2, -1/2 right there. And then -1, -1 is right there, really close together. So they're the green points. And then 1, 1 is right here, and then 2/2 is right there. So what's going to happen is, I could keep going for more points, and what you're going to see is that these numbers keep getting smaller and smaller and smaller, and then these numbers also keep getting smaller and smaller and smaller. And that means the y's are getting smaller and smaller and smaller. So they're going to get really close to the x-axis where y is 0. But as it turns out, there's no number I could put in here and get y to be 0. So I'm going to introduce you to our first wall, our first asymptote. And it's going to be right along the x-axis, which is saying where y is 0. And again, there's no number I could ever put in here and get y to be 0. In addition to a horizontal asymptote, we're actually going to have a vertical asymptote, because as it turns out, x can never be 0 either. I can't take 1 and ever divide it by 0. So we're going to have another wall here, and on this wall, this is where x is 0. So in the last two chapters, we had either a vertical or a horizontal asymptote, and in this chapter, we're going to have both. And now the shape that you saw happen up here is going to happen here. Okay, so if you look at just the positive numbers, as my x's got, ooh, you can't even see that, as my x's got bigger, my y's are getting smaller, right? And then I have this relationship over here as well. Okay? All right, let's talk about the domain and the range now. So because of these walls, these arrows, all these arrows on my shape are going to be impacted. So I'm going to just really emphasize those arrows. So let's start with this arrow. This arrow, as I approach it, is going right and it's going down. Nothing's going to stop it from going right, so it's going to keep going right, but it will get stopped going down at 0 at this asymptote. And now what I want you to do is come over and look at this wall, or this arrow. This one, as I get to that arrow, is going left and going up. Nothing's going to stop it from going left, but it will get stopped from going up. And I just want you to notice real quick that these are almost the same, except our infinity is negative here and positive here. And so you're going to see that same pattern happen with these arrows. So this arrow, as I work towards it, is going left and it's going up, but it will get stopped from going left at this wall, which is 0, but it won't get stopped going up. And then when you look at this arrow, as you're working towards this arrow, it's going right and going down. It will get stopped going right at this wall, but it won't get stopped going down, so negative infinity. So if you notice this pattern, these are almost the same, except a positive versus a negative infinity. So now when we talk about domain and range, we're going to have two domains and two ranges because we have two shapes. So for this shape, when I go for my domain, the smallest x is negative infinity and the biggest x is 0. And then the domain for this shape, my smallest x is 0 and my biggest x is infinity. And then when I do range, my smallest y and my biggest y, my smallest y here is negative infinity to 0. And then when I do the y's here, I go from 0 to infinity. Okay? So these walls, these asymptotes, are getting stopped. And just a reminder, the equation of this asymptote is x equals 0, and the equation of this asymptote is y equals 0. Because every point on this line has an x value of 0. That's 0, 0, 0, 1, 0, 2, 0, 3, 0, 4. So since x is always 0, it gets to name the line. We are going to not do those right now, really limit what we're doing in this chapter. So let's start to take a look at some of the transformations that are going to happen. So with that, sorry, I need to put it over here. we're going to reintroduce a, h, and k. So a is going to replace the 1, and h is going to be contained. It's always contained in something, and this time it's going to be contained in the denominator, and k is still just hanging out off to the side, adding or subtracting. And remember, this is where you'll see your stretch, compress, or flip. H is where you always take the opposite. That tells you to go left or right, and k tells you to go up or down. So right now, just looking at this one, this is my h. I will be moving left 2 and down 3. So what's going to happen is the parent function that we're going to graph is still the 1 over x. The additional numbers are here. So what's going to happen is this whole graph, everything is going to shift left 2 and down 3. So in the past, I've typically graphed the asymptotes last. I'm actually going to graph them first because I want to show you a little shortcut. So I'm going to take this wall, which is not affected by up or down, but it's affected by left or right, and I'm going to move it left 2. And just for future information, this is at x equals -2. And then I'm going to take this wall, which isn't affected by left or right, but up or down. So I'm going to move this one down 3. Oh, that's not very good. And for future references, this is y equals -3. And not only are the walls going to move, but the points, these points here are going to move. So rather than finding, for instance, 1, 1, and now moving left 2 and down 3, and it's going to end up here, a quick trick that you can do is take these new asymptotes and act like they are the x and y axis. And from here, if this is 0, 0, go to 1, 1, and you get the point. So let me show you this one more time. Technically 1, 1 is here, and I should go left 2, down 3. But if I move the walls, or the asymptotes, and they shift, they'll kind of automatically move the other points. I hope that makes sense. I'm not very good at explaining that. So, and then I'm going to take the other point, which is -1, -1, and just act like this is 0, 0, and go left 1, down 1. So I could graph the fractions. I don't really like graphing fractions because this is such a small space. So as long as I know the shape, I'm good here. And this shape will always happen. It's kind of like a boomerang shape. What's going to happen is these are going to be catty-corner from each other, diagonal from each other. They're never going to be side to side, so they'll never be both on top or both on right or both on bottom or both on left. They're always diagonal of each other. So now when we do the domain and range, this arrow is following the arrow. It's still going left and up, but it gets stopped going left at this wall of -2, but not going up. And then when you do this arrow, which is going right and down, it's going right, but it's going to get stopped going right at this wall, but it won't get stopped going down. So again, just notice these are the same. The only difference is the infinity positive or negative. And that same pattern will happen here. So this arrow, as you work towards it, is going right and down. Nothing will stop it from going right, but this wall, which is at -3, is going to stop it from going down. And this wall, or sorry, I keep saying that, arrow is going left and up, but it gets stopped going up, but it doesn't get stopped going left. So since it doesn't get stopped going left, it's -infinity, but it gets stopped going up. So here's one more thing to point out. If you notice, the wall is at x equals -2. That makes the x values -2. And then the other parts are your infinities. And then the wall here is at -3, and that replaces the y values. And then put the negative on that one. So now when we do our domain, we've got our smallest x and biggest x here. So let's see, 2, or -infinity to 2. And then for this, and I didn't put the negative there, and then this shape is -2 to infinity. So again, that trick is, it's all infinity here in here, but if you notice, the x's play a role, okay? The x's of the asymptotes. And then the range, smallest y to biggest y, I go from -infinity to -3. And this one, my y goes from -3 to infinity. So again, kind of pointing out this trick. is it's all infinity here, but the inner numbers are going to be the x value of the wall, because domain is x, and then it's negative infinity to infinity, but the inside numbers are going to be the y equation wall, so y equals -3. So let's take a look at this one, and then we'll see some with like stretch and compress and flip and all that. All right, so according to this, we're going right 1. Sorry, that phone's ringing, it's not mine, and we're going up 2. So what's going to happen is these points will all move right 1 up 2, and so will those walls. So I'm going to start with this wall, and this is affected by right 1. And then this wall is affected by up 2. And this equation is x equals 1, and this one is y equals 2. And now I'm just going to take the non-fraction points and I'm going to graph them. But remember, if the walls shift, if you treat this as your new 0, 0, then you can build in the shift of these points. So -1, -1, and 1, 1. And then make the curves catty-cornered. They all curve in to the center. All right? I'm going to skip the domain and the range on this one because we're going to try some other problems. So I'm going to flip over, and we're just going to do a little bit on the back, not too much because, again, we don't have time at the end of the year to get through all of this. All right, so let's start with a very basic function. Let's just take the 6 over x. So just writing this out again. We're going to have our stretch and compress here. So our parent function is going to be stretching by 6. So what we're going to do is we're going to make our table, put my numbers in, and from here on out, we will be graphing our table. We're going to build our stretch in, because normally what we would do is we would graph the parent function, so let me flip back, and then we would take our stretch, compress, flip, and we would make a new y column. So we're going to skip that step, and we're actually just going to build it right in. So we're going to graph everything but the h and k. So I'm going to make my table out of this. So 6 over -2 is -3, 6 over -1 is -6, 0 will not work, and then 6 over 1 is 6, and 6 over 2 is 3. Now there are no h and k's, so my walls will stay where they are on the original x and y axis. And now I'm going to graph -2, -3, and I'm going to graph -1, -6, and I'm going to make my curve. I didn't hit that point, but that's okay. And then I'll graph 1, 6, and 2, 3, and graph that curve. All right, just a reminder of the arrows. This one's going left, not getting stopped, but it's going to get stopped going up at 0. This arrow is going right and down. It will get stopped going right, but it will not get stopped going down. And then this arrow is going left and up. It will get stopped going left, but not up. And this arrow is going right and down. It will not be stopped going right, but it will get stopped going down. So again, the trick is look at the top and the bottom. The number's consistent, but the infinities change. And then left and right, the numbers are the same, but the infinities change from negative and positive. So when we do this one, here we go, putting those x values in. This time we're going to have a flip, that's the negative. We're going to have a stretch of 3, that's the 3, and we're going to have a left 2. And we're going to take the a, we're going to make our table out of a over x. So a over x. So I'll make my table out of -3 over whatever my x value happens to be. So if I put -2 in here, I get 1.5. If I put -1 in here, I get 3. 0 still will not work. And then if I put 1 in there, I get -3 and then -1.5. So let's talk about our walls. So first, this wall is affected by left, right, so it's going to move left 2. But there's nothing affecting the horizontal asymptote, so it's going to go right along the x-axis. So remember, the general shape, all right? this is what the parent function looks like. This time there's a flip, and everything flips over the x-axis. So this one's going to come down, and this one's going to go up. So instead of being in the first and the third quadrant, they are in the second and fourth quadrant. Always catty-corner from each other, always going towards each other in that center. So where my shape would have been here, you're going to see it's down here now. So -2, -1.5, sorry, over here. So it was here, now it's going to be up here. So -2, starting this my center, -1.5, we'll put it right about there. I wouldn't typically graph that decimal, but I will. And then -1, 3, and there's my first curve. And then 1, -3, and 2, -1.5. So again, when I did that, I treated this as the center, and now I'm going to graph my curves. So again, the shape had been here, it flips up there, and the shape had been here, it flips to down here. Okay? All right, let's go to the last one. We'll do another set of arrows. I'll leave the arrows off of this one. Oh, actually, no, that's all we're going to do here. So with this one, this arrow is going right, but it's going to get stopped at -2, and it's going up, which will not stop it. This arrow is going left, which won't get stopped, but it will get stopped going down at 0. This arrow is going right, nothing stopping it, but it gets stopped going up at 0. And this arrow is going left, but it gets stopped again at that -2, but it won't get stopped going down. And that is all we're going to cover in this first set of notes. All right, so check Schoology to see what those practice problems were.